Imagine it's the IPL final. Millions of users are trying to book tickets. Everything looks normal, then suddenly your main database crashes. Not slows down, not becomes overloaded. Here we are talking about it completely dying. What happens next? For most applications, users see errors, revenue stops. Social media will explode. Engineers get emergency calls at 3 a.m. But somehow, companies like Google, Netflix, survive these failures every single day. Servers die, hard drives fail, entire data systems go offline. Yet, most users never even notice. How? Today, we are going to learn one of the most important concepts in system design, availability. And by the end of this video, you will understand how modern systems stay alive even when everything seems to be falling apart. Think about a hospital emergency room. Maybe some equipment is unavailable. Maybe the most experienced doctor is not present. Maybe a fewer systems are temporarily down, but patients are still treated. The hospital continues operating. And similarly, this concept is followed by availability. A system is available if users can continue using it when they need it. Even when some components fail, availability is commonly measured in terms of nines. So as you can see in this image, we are showing three different types of ability. 99%, 99.9%, and this is what we call the famous five nines. The higher the number, the less downtime users experience. So if my system is 99.9% available, it means it will have a downtime of approximately 9 hours per year. Now, many engineers confuse the availability with reliability. Now, they are related, but they are not same. Availability asks, can users access the system? But reliability asks that the system consistently behave correctly. Now, let's take an example. Imagine a food delivery app. If it's available but occasionally charges users twice, it is available but not reliable. You see the Zomato charging extra fees, like calling it the surge fees. The main idea behind this is the engineering. In case of very high users, the seeing the surcharge, the users ordering the food will drop down, thus minimal impact on the engineering system. If it's perfectly accurate but goes down every weekend, like it is reliable but when running but not highly available. Big tech companies need both. Now, to understand the failures, let's first understand the dependencies. We have two types of dependencies, series and parallel. Think about taking an international flight. You must complete check-in, security, immigration, boarding, and if one of these steps fail, right, you will miss the flight. Now, this is called the series dependencies. In software systems, users send the request to database and then you get the payment service, right? Every component must work. One failure can stop the entire flow. But now think of supermarket checkout counters. Maybe 10 counters are open. One counter breaks. Do customers stop shopping? No, they move to another counter. This is what we call parallel dependency. The system fails only if every counter fails simultaneously, which is much less likely, right? The idea is the foundation of high availability. Failures are normal, not exceptional. Let's look at some of the most common ones. First is hardware failures. Hard drive crash, right? Power supplies fail, servers overheat, or hardware eventually breaks, right? It's not a question of it is a question of when. Some are software failures, a bad deployment, memory leak, sometimes a deadlock. Software causes more outages than the hardware ones. And the last we could have the network failures, right? Packets get lost, latency spikes, services become unreachable. Many large outages begin with network problems only. Now, the question comes, how do we survive these failures? Simple. Don't rely on one thing. Simple as that. Create backups. This is what we call the redundancy in terms of software systems. But here's a mistake many engineers make. They create redundancy in only one layer. How? Imagine there are 10 application servers, one database. If that database dies, everything dies, right? Those 10 servers become useless. Redundancy must exist at every critical layer. Application layer, database layer, all the layers that we talked about in the last video, they should have some redundancy. Otherwise, you will only move the bottleneck. Now, the simple redundancy model is active passive. Think about the spare tire in your car. Most of the time, it is like not useful, it does nothing. But when the main tire fails, it saves the day, right? You feel like, oh, thank God we have that tire. In software, one system handles the traffic and another waits as backup. Now, this is what we call the active passive mechanism. Now, there could be three common ways of doing the standby. We have one cold standby, means the backup is completely offline, which is the cheapest, right? Slowest recovery. Then we have the warm standby, which is running, but it is not actively running the traffic. Moderate recovery time. And then we have the hot standby, fully synchronized, ready immediately, and fastest recovery. Databases commonly use active passive architectures. There is another one which is active active. Now imagine a supermarket checkout lanes. Every counter is actively serving customers. If one counter closes, customer moves somewhere else. That's active active. All systems work simultaneously, no special failover process. Now this is commonly used for like web servers, your APIs, because these systems are usually stateless. Any server can process any request. So what are the challenges with stateful systems, right? Stateful systems are harder. A user's data may exist on only one machine. So to support the active-active, we will definitely need a shared storage like a Redis or maybe a distributed storage, or you have sticky sessions, right? But sticky sessions reduce availability because users become tied to specific servers. So far, we have only assumed, right? Only a server fails. What if the entire data center fails? Power outage, flood, bomb blast, or network outage. Now every server in that location disappears. Now this is where geographical redundancy comes in. Think of banks. They don't operate from one branch, right? They have branches everywhere. Software systems do the same. So there could be different types of ways you can define geographical redundancy. So we have like multi-zone. Data centers in different regions is multi-region. And third, we have multi-cloud. So what is multi-zone? It's like multiple branches in the same city, as shown in this example as well. If one branch closes, you go to nearby zone and get the data. Multi-region. It's like you are having the data centers in different cities like Delhi, Mumbai, and maybe somewhere in London, Singapore, or where. If one region fails, another survives. Multi-cloud is like using multiple cloud providers, AWS, AGP, GCP, Azure. And if one provider experiences issues, like they are having some outage at their end, the application will remain available, right? Now, multi-region systems, but there's a default or disadvantage, like multi-region systems introduce business decisions, right? Two important metrics, RPO and RTO. RPO is recovery point objective. How much data loss is acceptable? 1 minute, 1 hour, or 1 minute? RTO says recovery time objective. How long can the system remain unavailable before recovery? Now, these are not purely technical decisions, right? They have to be made by business involvement. They directly impact revenue and customer trust. So we really need to understand how to define this R2 R2, and similarly on that basis we define the multi-regions. So let's understand some of the big tech decision patterns that are used by them to ensure the high availability. First is like load balancer and health checks. Load balancers continuously check server health. Are you alive? Are you healthy? And if a server stops responding, traffic automatically moves elsewhere. Users never notice. Next could be database replication. Primary database, then we have multiple replicas. And we could have automatic failover to those replicas. Now, there could be two types of replication models, synchronous or asynchronous. Asynchronous says that only when the data is matched or replicated or same data is updated in my replicated database, then only I will move on to next write. This is synchronous. So it has like higher latency, right? Asynchronous says that as soon as we have written the data in the updated the data in the primary database, we do not care if it goes to the replicas or not. There could be possible data loss, but we have the maximum availability. Semi-synchronous also exists like a middle ground. It depends on the requirements of your system. Next, we could have queue-based load leveling. Think of a restaurant order tickets, right? Orders enter the queue, kitchen processes them when ready. Queues absorb traffic spikes, prevent overload, and they overall improve the availability. And the last, we have circuit breakers. Imagine an electrical circuit breaker, right? Too much current, it disconnects automatically. Software circuit breakers do the same. If a downstream service keeps failing, right, stop any request to it, right? We will not wait for it to complete failover. So this helps to prevent cascading failures and protect the rest of the system. So today we understand like how high availability is not achieved with one technology. It achieved through layers of protection. Redundancy, failover, application, health check, circuit breaker, geographical distribution. Because